Imagine it is summer. The air feels warm on your skin. You are tending your crops. You are gathering food. You are watching your children play under a bright, familiar sun. Then, something changes. The sky, once a brilliant blue, turns a hazy, sickly yellow. The sun seems to fade, a pale, distant disk. Days that should be long and warm grow short and cold. A strange chill creeps into the air. Then, impossibly, snow begins to fall, blanketing the green summer landscape. This is not a science fiction scene. The culprit was not an alien invasion. It was not a celestial cataclysm. It was the planet itself. A single colossal volcano erupted, plunging the world into a prolonged winter. How could one volcano do this? How could it freeze the world? We must become detectives, looking for clues buried in time. This story is written not in books, but in the very fabric of our planet: geology, chemistry, human resilience. A supervolcano, a geological feature of almost unimaginable power. Not a mountain merely blowing its top. The planet itself exhaling with cataclysmic force. Consequences rippled across the globe, affecting every living thing. The smallest microbe, the largest mammal, our early ancestors. The immediate aftermath would have been terrifying. A deafening roar, the ground shaking violently, a pillar of ash and gas rocketing into the sky, punching into the stratosphere. The stratosphere, the stable layer above our turbulent weather. Material reaching this height does not easily rain out. Instead, it spreads, carried by high-altitude winds. It forms a thin veil that encircles the planet, a gossamer-thin blanket that becomes the agent of a global climate crisis, a testament to the immense hidden power beneath our feet. So, what exactly did this volcano do to change the world's weather so drastically? The answer lies in what it threw into the sky. A super eruption doesn't just spew hot lava and rock, it blasts an enormous quantity of pulverized rock, ash, and gases high into the atmosphere. Think of it as a planetary-scale injection. The ash is the most visible component, turning day to night and burying entire landscapes. But the real climate changer is a gas you can't even see: sulfur dioxide. When the plume rockets into the stratosphere, the sulfur dioxide undergoes a transformation. It reacts with water vapor to form tiny droplets of sulfuric acid, sulfate aerosols. These particles are incredibly effective at reflecting sunlight. They act like a planetary sunshade, bouncing incoming solar radiation back into space. With less sunlight reaching the ground, the planet begins to cool. The effect is swift and relentless. Global averages can drop by several degrees Celsius. Even 1 degree matters. 5 or more is catastrophic. It disrupts weather patterns, alters jet streams, and sends seasons haywire. Summers fail to arrive. Monsoons can weaken or fail entirely. Unlike ash, stratospheric aerosols can linger for years. Expect 2 to 3 years of noticeable cooling. A true super eruption could mean 5, 6, even 10, followed by decades of instability. How can we possibly know about a weather event that happened 74,000 years ago? We don't have written records or ancient weather stations. Instead, we have nature's own archives. Scientists act as cosmic librarians, reading stories preserved in ancient ice and old trees. Ice cores from Greenland and Antarctica capture yearly snowfall in layers thousands of feet deep. Massive eruptions leave unmistakable sulfate spikes in these frozen timelines. A scientist lifts a core section. The chemistry reveals the blast and dates it with precision. Trees add a ring each year. Sunlit, warm, wet years make wide rings. Cold, dry, dim years make narrow ones. Following a major eruption, forests often record exceptionally thin or frost rings, a volcanic signature. When ice cores and tree rings align, the case becomes incredibly strong. For Toba, a massive sulfate spike around 74,000 years ago matches lake sediments and marine fossils. These records give voice to the deep past, the blast that turned summer into winter. In April 1815, Mount Tambora in present-day Indonesia exploded. The blast was heard over 1,600 miles away. It ejected an estimated 150 cubic kilometers of ash, rock, and gas deep into the stratosphere. The immediate effects were devastating locally, and the sulfur dioxide created a persistent aerosol veil that spread worldwide. 1816 became the year without a summer. New England and eastern Canada saw months of haze, a dim reddish sun, frosts, and even snow in June, July, and August. Crops failed repeatedly. Lake and river ice formed as far south as Pennsylvania. Europe endured cold and torrential rains, leading to crop failures, food shortages, riots, looting, and soaring grain prices. Famine and typhus followed, taking tens of thousands of lives. The gloom seeped into culture. Mary Shelley, with Lord Byron, was inspired to write Frankenstein. Tambora is our benchmark, yet it pales before prehistoric super-eruptions. Toba may have been 100 times more powerful. If Tambora reshaped a year, what would an event 100 times larger do to our world? Now let's journey back in time, to about 74,000 years ago, during the last ice age. This is the stage for the main event, the Toba super eruption. Sumatra, Indonesia. Toba on the map. Toba wasn't just a mountain, it was a massive magma chamber beneath the crust. When it blew, it erupted with a force almost beyond comprehension. One of the largest explosive eruptions in the last 2.5 million years. It blasted nearly 3,000 cubic kilometers of material. It left a massive caldera, now Lake Toba, over 60 miles long. The ash covered much of South Asia, including the entire Indian subcontinent. In many places, the ash was several inches thick. Closer in, it exceeded 20 feet. That ash is a timestamp, pinning sites to the immediate aftermath. Sulfur dioxide releases were colossal, thousands of times greater than Pinatubo 1991. That sulfur injection drives volcanic winter. Models simulate global averages dropping 3 to 5 degrees Celsius, with larger drops at high latitudes. A sudden shock to an already cool world. A decade of cold, lingering effects for centuries. It was, incredibly transformative. This brings us to the Toba catastrophe theory. A volcanic winter pushed humanity to the brink. Proponents point to mitochondrial DNA, passed from mother to child, suggesting descent from a small African population then, a population bottleneck. The theory says Toba reduced us to perhaps a few thousand. A decade-long winter, food sources collapsing, only the resilient, adaptable, or lucky survived, sheltering in refugia like certain coastlines. Those survivors later seeded global expansion, but archaeology shows continuity. In India, tools appear both above and below the ash. African sites show people persisted. Many argue the impact was uneven, severe, not uniformly catastrophic. The detective story continues. Human ingenuity, shifting foods, cooperation, technology, may have bridged the cold years. Geology, archaeology, genetics, converging lines, contested narratives, and an open question about our deep past. Let's get back to the fundamental physics of how a volcano can act as a global refrigerator. It all comes down to Earth's energy budget. Some energy reflects off clouds and ice, much is absorbed by land, oceans, and atmosphere, warming our world. The planet radiates heat to space. Stability demands energy in equals energy out. A large eruption throws that balance off. Sulfate aerosols are highly reflective to incoming shortwave, boosting Earth's albedo. It's like putting a semi-transparent mirror between Sun and Earth. Surface and troposphere cool, while the stratosphere, where aerosols reside, actually warms. Unlike CO2, aerosols don't trap much outgoing infrared. The net effect is cooling. In the dry, stable stratosphere, droplets persist for years. After Pinatubo, cooling of Trauen in Traum 5 degrees lasted about 2 years. A monster like Toba could sustain far more sulfur, prolonging the sunshade and the chill for much of a decade. The global cooling and reduced sunlight trigger a cascade of impacts. Photosynthesis, life's engine, sputters. Plant growth slows or stops. Agriculture and ecosystems reel. Herbivores find less to eat. Insects and mammoths alike suffer. Starvation spreads, reproduction declines, populations crash. Carnivores and omnivores, including early humans, face scarcity. The adaptable switch foods or migrate to less affected areas. Cooling reduces ocean evaporation. With less moisture aloft, clouds thin and rains falter. Monsoons can fail. Tropical and subtropical regions endure severe drought. Altered gradients shift storm tracks, bringing unseasonable snow and rain to others. Intense stress favors generalists over specialists. For humans, social cohesion, planning, and flexible technology improve survival. Coastal groups turn to marine resources. Crisis spurs innovation and cooperation, traits that define our species. The story of the blast that turned summer into winter is more than a chilling tale. It is a lesson about our planet and our relationship with it. A single event in Indonesia can alter climate and life across the globe. Atmosphere, oceans, and life are in constant dialogue. We are subject to geology's immense power. Planetary-scale events are rare, but recur throughout Earth's history. The second lesson is resilience. Life is tenacious. Toba did not sterilize the planet. The veil cleared, the sun returned, life recovered, plants regrew, animals rebounded, and humanity survived. We endure by using tools, communicating, cooperating, and learning. Today we have the power of science. Satellites, seismometers, gas sensors, and ground deformation to warn us. We cannot prevent a super eruption, but warning lets us plan, mitigate, and prepare supplies and infrastructure. Learning from Tambora and Toba is essential to resilience. Ash and trapped sulfate are not curiosities. They are an instruction manual for stewardship. The sun's light travels 93 million miles to warm us, but its warmth is not guaranteed. A thin veil from Earth's inner fire can dim it and change our world. The volcanic winter is a humbling reminder of nature's power and our vulnerability, but it is also a story of hope. Ancestors looked up at a faded sun and found a way to endure, passing the torch forward until the day the sun shone brightly once again. Remember the journey of sunlight and the lessons written in ash and ice.